In this presentation, we are going to introduce the characterization of lime mortar and brick used in a 16th century cistern. The case, Order of Santo Domingo Convent in Dominican Republic. The research has been developed by Virginia Flores Sasso, Sagrario Martínez Ramírez, Esteban Prieto Vicioso, Gloria Pérez, Letzay Ruiz Valero, and Paula Carmona Quiroga. This presentation is structured with introduction, objective, methodology, results and discussion, and conclusions. Two of the most popular materials that compose the architectural heritage are mortars and bricks, as they were used to build historic structures. Historic mortars and bricks have proven to be durable during the years and very compatible with historic structural units. However, different environmental and human factors can accelerate their deterioration. In this way, it is important to characterize the materials used in these walls to generate new mortars and bricks with the same or similar characteristics that can be used for the restoration of these buildings. Therefore, the aim of this research is to characterize the lime mortar and brick used in the cistern of Santo Domingo Convent in Dominican Republic, built in the beginning of the 16th century in the Hispaniola island. The cistern of Santo Domingo Convent. The Order of Preachers, or Santo Domingo, arrived in 1510, and the construction of their convent began in 1511, and that of the church in 1516. By 1544, the convent complex was already finished. The convent complex was enclosed by a crenellated wall, and its interior housed the convent or friar's residence, a church with an atrium, a chapel of the Dominican Third Order, and ushered two cisterns and the Real and Pontificia Universidad de Santo Domingo de Aquino. In the convent, there are two cisterns, a small semi-buried one and a very large cistern that is the object of this study. The cistern has a rectangular floor plan of 3.78 meters wide, 12.60 meters long, and 3.36 meters high at its highest point, and it is covered by a brick vault following the models of the Roman and Mudéjar cisterns. The vault is formed by bricks of 29 by 14 by 5 centimeters placed in sardinel and joined with lime mortar. It was customary to have the inner walls lined with lime mortar, sand, red clay, with iron oxide to prevent filtrations and water putrefaction. The vault has three openings, one in the center with a hexagonal shape, another for the entrance of rainwater, and the last one that would be the equivalent to the opening of a well or curbstone. To carry out this investigation, two samples of joint mortar and one sample of brick were taken. For the joint mortar, the highest part of the brick vault was selected, and the samples were taken from the depth of 12 centimeters. The brick sample was taken from one brick that was next to the mortar sample. Initially, the samples were cut out into two pieces. The larger ones were ground for the analysis, and the others were left whole, which were photographed on both sides. A series of laboratory studies were carried out. X-ray diffraction, differential thermal and thermogravimetric analysis, X-ray fluorescence, and Fourier transform infrared spectroscopy. The mineralogical characterization of lime mortar, AJ1 by XRD identifies the presence of calcite, CSH gel, turbomorite, and quartz. In sample AJ2, the major phase is quartz followed by calcites and plagioclase. The majority mineralogical phases identified in the brick. AJ3 are quartz, plagioclase, and hematite. DTA/TG curves of both mortars confirming the presence of calcite by the sharp weight loss at higher temperatures and the associated endothermic peak of the heat flow at 750/786 Celsius. We have two types of mortars, one in which the binder is lime and the other in which the binder, in addition to lime, has another component that is probably a silicon mineral. In the case of X-ray fluorescence, AJ1 mortar has a higher Ca content than AJ2, and the latter has a higher content of Si, A1 and Fe, which confirms that the mortar AJ2 has another component in the binder in addition to CaCO3. The element composition of the brick confirms the presence of Si, A1, and Fe with low Ca percentage. The FTIR shows that sample AJ1 shows the characteristic signals of calcite and quartz, as well as an intense signal at 969 centimeters -1 that is associated with the stretching vibrations of the SiO groups of hydrated calcium silicates, CSH gel. Mortar AJ2, the signal at 1436 centimeters -1 due to the vibration of the CO2 -2 groups. The calcium carbonate is of very low intensity. However, it presents signals characteristic of kaolinite and quartz. In the case of the brick AJ3, the most intense signal corresponds to quartz, together with a sharp signal due to the presence of nitrates from the same environmental contamination. Likewise, this sample presents an intense signal at 1048 centimeters -1 that is associated with the vibrations of SiO groups in clay minerals. We can conclude that the analysis confirmed that we have two types of mortars, one in which the binder is lime 60% and calcium silicate hydrate, probably formed by a pozzolanic reaction to reduce the porosity and increase the hydrolicity of the mortar. In the other mortar, the binder, in addition to lime, which is 15%, has another component that is a silicon, iron, aluminum mineral. Thank you very much.